we're going to do a little lab activity, a very simple lab activity, to try and see if the impulse momentum theorem and conservation of momentum give us a correct prediction. And it will. I'll just let you know. I'm spoiling it. Spoiler alert. Yeah, this is going to work. But let's go over the setup and go over some of the theory first. So this is theory. Okay. So here's what you all have set up at your tables. You have a track, and hopefully at the end of each track you have a barrier of some kind, so that the cars won't slide onto the floor or whatever. And you've got two cars on there. Here's one of the cars. And I'm going to make this the plunger car, right? The car that's got the little plunger thing on it, like this one. Okay. It's got one of these little springy deals on here. And, that's cool. And then I made this a little too close. Let me move this over a little bit. So here's the little spring, and then here's the other car that doesn't have the plunger on it. Not drawing this very well, but here we go. There's the wheels. Now these wheels, they're very low friction wheels. I mean, if I, oh, that one's high friction. All right, if I spin these, there's really not a lot of friction. And I mean, there's some, but there's not a whole lot. So they'll roll, pretty good, but without slowing down. It takes them a long time to slow down. So now, what we're going to do is this. We're going to put all those masses, both of the bars, the little black bars you have, you're going to put both of them in here. We're going to call this car 1, and this is car 2. And you should know what M1 is, right? What is M1? It's the mass of this whole thing. And what is the whole thing? It's the two bars added together plus the mass of the car. Do you need to change it to kilograms? You can if you want to, but for this lab you don't have to. If you want to leave it in grams, go ahead. And then what you're going to do is you're going to take this plunger and you're going to put it all the way in. Now here's how you do that. Watch very carefully. You're going to take this plunger and you push it in, and then you kind of push it up this way. So it goes in and up, and it'll lock into place. But then if you take it like this and you tap on it, whoops, it'll come out like that. So you push it in, lock it into place, and then and that's how you're going to push these cars apart. So what we're going to do is you're going to push this in, and then you're going to we're going to say the position of the cars when the two cars are together with the plunger, pushed in like this. See, the plunger's pushed in before it comes out. This is going to be the initial position of both cars. We're going to measure the position of the cars from there. Now, when they push each other apart, what happens here? Here's car 1, and car 1 gets a force applied to it, right? It pushes outward, and they both apply a force. So this is the force of car 1 on car 2. The force of car 1 on car 2. But what happens to car 2? With this, due to this plunger thing, you get a force of car 2 on 1. And what do we notice? What must be true about these two forces? They are equal to each other, but in opposite directions, right? Newton's third law. For every force on one object, there must be an equal but opposite force on another object. That's Newton's third law. It is true. It has been verified. It is a fact of nature. Well, and also notice that while this is happening, we call this an explosion. An explosion is when you have two objects that have some kind of energy contained in them, or more than two objects. It can be any number of objects. And that energy, it can be released so that it pushes the objects apart. And that's why we call it an explosion. Now, there are real explosions, like a grenade or something, and there's chemical energy in there, and it releases all at once, and it throws fragments of metal in all directions. Okay. This is less violent. Okay. And so these cars are just going to go boom, like that. Now, these interactions of forces happen for the same amount of time, don't they? Bam! Okay, then they come apart. So the amount of time that these forces, so we can say, well, the force on car 1 is equal but opposite to the force on car 2. But they both happen for the same amount of time. That is, the time that this force is applied is exactly the same amount of time as this force is applied. You know, right? I mean, it makes sense. But we say force times time is impulse, and impulse is the change in momentum. So we're going to say, hey, the change in momentum of car 1 should be equal, but in the opposite direction as the change in momentum of car 2. This negative just means direction. Let's put vector hats on these. Well, let's. So this is the mass times the change in velocity of car 1 equals the negative m2 delta v2. Well, now I'm going to expand this out, and forgive me for the mathematical tediousness, and we have to kind of hurry. This is going to be V1 minus V0, right? What is V0 for both of these cars? 0. So equals negative M2 V2 minus V0. This is 0, this is 0. So we have this. We have M1 V1 should be equal to negative M2 V2. And these are the velocities of the cars after the plunger has done its thing and they're moving apart. Does everybody see that? Well, what we're going to do is we're going to say that this V1 right here, this velocity after it's fired, we're going to pretend that it's pretty much constant as the car goes across the track. And what we're going to do is we're going to say that this M1, well, M1, V1 is going to be delta x1 over delta t1. Now this delta t is different than the delta t that we had up here. This is the delta t while the plunger is coming out. It's a very short period of time. But this is the time that car 1 is moving until it hits this barrier. Okay, so car 1 is going to hit this barrier right here. And it's going to go, they're going to blow apart, and it's going to move over here, and it's going to go thunk against your textbook or whatever at the end of the track. So how far did the car move? Well, the car moved from, well, here's x final. Let me erase this. So we'll say this is M1. Well, here's x initial all the way to x final. X final is right here. How come I didn't make x final all the way over here on the end of the track? Because if I say x initial is right here, the car moved from here to here. If you're measuring it from this part of the car, you have to measure the final position from this part of the car. You don't want to add the length of the car to the displacement of the car. Yes? Now listen to me very carefully. If this lab is going to work, you have to really make sure that you start from the very middle where both cars are, and you go to here. Not the end of the track, but to here. Okay? And then this car is going to go all the way over here. And so we want to go from X initial all the way over to here. So this is X final for car 2. This is X final for car 1. Now, if we do something very clever, what if we choose a spot right here so that when the cars move, they hit the end of the track at exactly the same time? So when they go apart, they go thunk. Now when this one goes from here, you'll hear a thunk when it hits the textbook. And then when you go from here, like thunk when it hits the barrier or the textbook, whatever you have there. Now, if we just put them in the middle or something and we blow them apart, this one will hit first and this one will hit last, so you'll hear a thunk thunk. Right? So you can tell, oh, it didn't take, but if you put it in just the right spot, they'll go apart and you'll hear a thunk. And that's what I want you to do, because here's what will happen. If you hear one thunk when they both hit at the same time, delta T1 and delta T2 are the same. And so they will cancel out. So here's what we're saying. The theory makes a prediction. This is we're making a prediction here. We're saying that M1 times delta X1 should be equal, but in the opposite direction, of M2 delta X2. Now one of the delta X's will be negative. Notice that on your track you have a number line to measure the initial position and final position in centimeters. It's okay to do this in centimeters. You don't have to convert to centimeters to meters. You don't have to convert grams to kilograms. If you want to, you can. It won't matter as long as you're consistent. But this should be equal to this. Is it? But is it? So that's what I want you to do right now. I want you to put the cars together just the way I showed. Let them blow each other apart and figure out what the initial and final positions are for delta X1 and delta X2. They'll both have the same initial position, but their final position, one will be over here and one will be over here. And then just record these, and then we'll analyze it. You can say, hey, if I multiply this times this, does it equal this times this? You know, after you collect your data, we'll analyze if it really did. Does everybody understand what to do? Oh, you've got plenty of time to do it. Go!